Hello, ladies and gentlemen. Welcome back. We are on day 2 of chapter 10.1. All right, let's go ahead and get rolling here. So we're going to just do pretty much more of the same with another example in there. First of all, I want to go through the conditions again. All right. So remember, conditions for inference about a population mean. Again, simple random sample. Has to be normal. And check for independence. Okay, I'm not going to repeat all of that is said. Please review that. We're going to be using the Inference Toolbox. Remember, there's 4 steps. There's the parameter, identify the population of interest, check the conditions. That was just what we looked at. Do the calculations, and then do the interpretation. Okay? Now, this is in your book. Again, I have to emphasize, ladies and gentlemen, please, please, please look at all of the examples in your book. All right? All right, let's see if I can make this fit just a little bit better. No, let's go with, okay, yeah, well, let's just go fit to the width. All right, that looks better. All right, so here we go. So video screen tension. 1, construct a confidence interval for mu. All right, so let's go through this. We've got a manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Okay, some variation is inherent in the production process. Careful study has shown that when the process is operating properly, the standard deviation of the tension reading is 43 millivolts. Here is the tension reading for a simple random sample of 20 screens from a single day's production. All right, there they are. Our job is to construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. Okay, this day. Parameter. Remember parameter. Identify the population of interest. Okay, so there's step 1. Okay, so here's the answer. The population of interest is all of the video terminals produced on the day in question. You need to be specific. When are they produced? Which ones are we looking at? Are we looking at everything produced for the whole year? Are we looking at the ones produced in January? Are we looking for the ones produced the first week of March? No, we're looking at the ones that are this day, in question on that day. So, continuing, we want to estimate mu, the mean tension of all these screens. Step number 2, conditions. Verify the conditions. Okay, now let's look at this very carefully. Since we know the standard deviation, we should use the confidence interval for a population mean that was just introduced to estimate mu. Okay, now we must check the 3 required conditions. Okay, that's not part of the answer. Okay, here are the conditions. Here we go. Simple random sample. Okay, we are told that the data, don't just say we are told. Okay, no. Be a little bit more detailed. We are told that the data come from a simple random sample of 20 screens from the population of all screens produced that day. See how detailed that was? Normality. Is the sampling, so this is the question you're asking yourself. That's not part of the answer. Okay, is the sampling distribution X bar approximately normal? Okay, past experience suggests that the tension readings of the screens produced on a single day follow a normal distribution quite closely. If the population distribution is normal, the sampling distribution of X bar will be, they should have in there, approximately normal. But what if the population distribution weren't not known to be normal? Okay, now this is what we do if that was not known. The sample size is too small to use the central limit theorem. So we examine the data, sample data. A box plot of the tension readings, which we'll look at here shortly, show no outliers or skewness. So we took the data and made a box and whisker plot. Okay, They also, now you don't have to do both. You pick one or the other. Okay, you can either do a box and whisker plot or a normal probability plot. It tells us the sampling data is approximately normally distributed, okay, because it's going to be fairly linear. You'll see in a second here. These data give us no reason to doubt the normality from which they came. Okay, so here is the normality piece, folks. So you would have to pick one or the other. So the box and whisker, you can see that it's fairly symmetric. This tells us that the sampling distribution is approximately normal. Okay, or you could do the probability plot. Remember on your calculator, ladies and gentlemen, when you go, when you go and you pick, okay, remember the sixth one. Let me just go down. So there's your scatter plot, and so on. There's your box and whisker plot. Remember to always pick the first one because it shows outliers. Okay, which we will need to review that stuff before the AP test. And then that sixth one, this one right here, that's your normal probability plot. Okay, go back to chapter 2 and review that if you need to. If that probability plot is fairly linear, okay, that's what tells us, ladies and gentlemen, it is fairly linear. This tells us that the sample distribution is approximately normal. Okay, so that was the normality piece. Okay, so that's what we said in here. Oops, a little bit further down. Right down here. These data give us no reason to doubt the normality of the population from which they came, because the sample data are approximately normal based on the box and whisker plot or based on the normal probability plot. Okay? Then the independence, remember you need your population needs to be at least 10 times your sample size. Since we are sampling without replacement, we assume that at least 200 video terminals were produced on this day because your sample size is 20. So we're going to assume that 10 times the 20, that, okay, at least 200 were produced that day. Okay, then step 3 is where you do your calculations. Now, again, there's a lot of writing here that you don't have to put in there. You just need to show your work. Okay, so this would be showing your work, folks. Remember what I said earlier. Okay, you got to recognize your formula. Okay, your X bar, that is your estimate. And then plus or minus your Z star. Okay, that's from the 90% confidence interval. Remember that comes from table B. At the bottom, that's where that 1.645 comes from. 43 is the standard deviation, or 0.43 is the standard, no, 43, and then divided by the square root of 20. And then your conclusion, ladies and gentlemen. Okay, I've got a reminder of myself down here what to do next. All right, this is my second video today, and it's 7:15 in the morning. So this is what we say. We are 90% confident that the true mean tension in the entire batch of video terminals produced that day is between 290.5 and 322.1 millivolts. Okay, boom, we're done. Now, little note, notice that our conclusion about the plausible values for mu connects directly to our work in step 3 and is given in the context of this problem. Be sure to include all 3 of these elements in step 4. So that's why look at all of the examples, look at how they are writing things and practice it. Okay, practice it. And I will do my best when we do our problems in class to model it. All right, and then I'll try to model it with our example here. Okay, I believe, oh, nope, let's do this. Okay, I'm going to go through these really quick, and then I'm going to go do this last example. All right, so how confidence intervals behave. These are all out of your book, folks. The confidence interval for the mean of the population illustrates several important properties that are shared by all confidence intervals in common use. The user chooses the confidence level, and the margin of error follows from this choice. We would like high confidence and also small margin of error. High confidence says that our method almost always gives correct answers. A small margin of error says that we have pinned down the parameter quite precisely. The margin of error is, okay, so your margin of error is the z-score, or z-star, your critical value, times the standard deviation. The expression of z-star and the standard deviation in the numerator and the square root of n in the denominator, so the margin of error gets smaller. When? Z-star gets smaller. So if our critical value gets smaller, okay, then obviously it's going to get smaller. Is the same as smaller confidence. There is a trade-off between the confidence level and the margin of error. To obtain a smaller margin of error from the same data, you must be willing to accept lower confidence. Okay, smaller confidence brings it in. So you must be willing to accept that lower confidence. You're more often to miss the mean in your confidence interval because it shrinks it, okay? The standard deviation gets smaller. The standard deviation measures the variation in the population. You can think of the variation among individuals in the population as noise that obscure the average value mu. It is easier to pin down mu when the standard deviation, sigma, is small. Reducing sigma is very difficult in practice, however. They like to ask questions about these. What's your knowledge of how things affect your confidence interval? Okay, and they love asking these types of questions, especially on the multiple choice portion. N gets smaller. Increasing the sample size and reduces the margin of error for any fixed confidence interval. Okay, that one, you should know that from the very beginning, that a bigger sample size is always better, and it's going to shrink your margin of error, okay, because you're dividing by the square root of it, right? Because we take the square root of n, we must take 4 times, this is a nice important fact, folks, you must take 4 times as many observations in order to cut the margin of error in half. I think I mentioned that on the other video. All right, there are a bunch of cautions. Again, these are right out of your book, folks, okay? Taking observations costs time and money. The required sample size may be impossibly expensive. Notice that it is the size of the sample that determines the margin of error. The size of the population does not influence the sample size we need. The size of the population does not influence the sample size we need. Okay, next caution. Any method of inference is correct only in specific circumstances. If statistical procedures carried warning labels like these on drugs, most inference methods would have long labels indeed. Our handy recipe, x bar plus or minus z star times the standard deviation divided by the square root of n, for estimating an unknown population mean comes from the following list of warnings to users. Okay, first one, the data must be a simple random sample of the population. Okay, I'm not going to read through all of that. You read it. Find it in your book or pause the video and read through it. Next caution. Different methods are needed for different designs. Next caution. There is no correct method for inference from data haphazardly collected with bias or unknown size. Next caution. Outliers can distort the results. Next one, the shape of the population distribution matters. And then the next one, you must know the standard deviation sigma of the population. This unrealistic requirement renders the interval of little use in statistical practice. Oh my goodness, Mr. I, are you serious? We learned all about that and then it's of little use. That's what we're going to do in chapter 10.2 and 10.3. Because it's not realistic to know the standard deviation of the population, okay? That's where the table B and the T distribution is going to come in. That's what we're going to be doing in chapter 10.2. But for now, we know it. All right, let's get to this example. I believe that is it because the next page, nope, one more caution. Yep, one more caution here. The margin of error in a confidence interval covers only random sampling errors. Ooh, that's a big one. The margin of error in a confidence interval covers only random sampling errors. It does not cover any other type of errors. All right. So again, those are in your book. Yep, that's the next chapter, so I'm not going to go there. All right, folks, here we go. Let's look at this last example. All right, let's go through our details here. So suppose your class, too bad we weren't in class, because if nobody had any peanut allergies or anything, you know, I could hand out these candy bars and it would all be great. We'd have fun eating them, etc. But unfortunately we can't. So suppose your class is investigating the weights of Snickers 1 ounce fun-size candy bars to see if customers are getting full value of their money. Assume that the weights are normally distributed with standard deviation of 0.005. Again, it's not realistic that we know that, but we're going to say that we do. Several candy bars are randomly selected and weighed with sensitive balances borrowed from the physics lab. The weights are 0.95, 1.02, 0.98, 0.97, 1.05, 1.01, 0.98, and 1 ounces. We want to determine a 90% confidence interval for the true mean mu. Okay, so determine Z star. Well, think about this, ladies and gentlemen. Okay, I don't have table B pulled up, but if we pulled up table B, oh, I guess I could pull up table B really quick, go through all of my stuff here. So let me pull up table B. I've got so many files. You would just be amazed how many files I have. All right, sorry, I should have had this pulled up earlier. So let me go ahead and pull up table B. There we go. All right, table B, ladies and gentlemen. Just like that, I got table B. All right, so remember at the bottom of the table, okay, this is where we are finding our critical value. So we're going to 90%. And it's 1.645. So that is our critical value. So Z star is 1.645. Okay, so 90%, remember, so I'm going to go ahead and mark, I'm going to go 1, 2, 3, 1, 2, 3. So 1.645 in either direction, it's going to be right about here. So this is negative 1.645 to positive 1.645. And ladies and gentlemen, that is where your 90% confidence is. So that's going to be the width of your confidence interval from negative 1.645 standard deviations below to 1.645 standard deviations above. All right. Calculate and interpret confidence intervals for the mean weight of candy bars. Follow the inference toolbox. All right, so step 1, remember, we begin with the parameter. So we want to estimate the actual mean weight. Let me get my little symbols up here. Mu, oh, my picture's in the way here. Mu, whoops, oh, never mind, showed up. All right, whoops, and I spelled weight wrong here. Of all Snickers 1 ounce, again, be specific of what we're looking at, 1 ounce fun size, why they're fun size, I have no idea, candy bars. Boom, step 1 is done. Okay, step number 2. Okay, first of all, we're going to check the simple random samples. Okay, well, if we look at the problem again, it does state, ladies and gentlemen, the candy bars are randomly selected. Okay, well, that's what we need. My apologies. The candy bars are randomly selected. They're randomly selected, but we do not know if they are an SRS, simple random. We don't know if they're a simple random sample. They're randomly selected, but we don't know if it's a simple random sample, but that's okay. All right. The next thing is normality. All right, normality. Since the population of weights is normally distributed, the sample distribution of X bar, okay, I'm going to do this because I can't put that bar above it. X bar will also be approximately normal. Okay, and then independence, ladies and gentlemen, the weights, let me switch colors, whoops. Well, let's go with, okay, independence, let's go, I'll do that green. Okay, the weights of the individual candy bars should represent independent measurements, period. Also, n is greater than 10n since there are at least 80 candy bars in the population. All right, so we've got our simple random sample. The candy bars are randomly selected, but we don't know if they are an SRS, a simple random sample, but that's it. They're randomly selected. Since the population weights, that's what happens when I type too fast. Since the population weights is normally distributed, the sample distribution of X bar will also be approximately normal, okay? The weights of the individual candy bars should represent independent measurements. Also, the population is greater than 10 times n, since there are at least 80 candy bars in the population. All right, step 2 is done. Now we're going to go to step 3. Step 3, we are going to do our calculations. All right. Now, the X bar, so I'm going to write down some of the key information that I have, folks. So these are the numbers that I'm going to be using. I know X bar, okay, so I took those samples, I added them up, and I divided by how many there are. Okay, and our X bar is 0.995. Again, add them up, divide by how many there are, and you get 0.995. We know the critical value, Z star, is for 90% is 1.645. Okay, we know that the standard deviation is 0.005. I'm just writing these down. This is actually, you don't have to show this on a test or on my test or on the AP test. You can go right to the formula if you want, but I always like writing things down on the side because it certainly doesn't hurt. And my sample size is, how many were there, ladies and gentlemen? Let's see, 8. There were 8. Okay, so here we go. So x bar plus or minus z star times the standard deviation divided by the square root of n. So I've identified the formula that I'm using. So here we go, 0.95995 plus or minus 1.645 times the 0.005 divided by the square root of 8. Okay, you plugged your numbers in, you've shown everything, got it down, and then you can go right to the answer. So I'm not going to take time to type that into the calculator. You can type it in, but you should get, I believe, 0.9921 to 0.9979. So that is step 3, showing the calculations. Okay, and then step 4 is our conclusion. Here we go, ladies and gentlemen. So we're going to conclude. Okay, hold on here. There we go. Okay, we are 90% confident that the actual mean weight of Snickers 1 ounce candy bars is between 0.9221 and 0.9979 ounces. Don't forget to include that type of measurement. So what else could we say here based on that? You know, they're saying they're 1 ounce size, fun size candy bars, but look, we're 90% confident that the candy bars are in that weight, right? So I'm going to say it looks like the company is exaggerating the weights. Okay. All right. You don't have to add that on there. That first sentence is good enough. Okay, but if they ask, what do you think? Well, I'm 90% confident that no, your candy bars are not saying what they're not weighing what they're supposed to weigh. Okay, now think about this, folks. If we went to a higher confidence level, if let's say we went to 95%, we'd have to use a bigger critical value, right? So that means we would widen that confidence interval a little bit, and it would probably capture that 1 inside that interval. Barely. Okay, barely. If we went 99%, that's going to get even wider, and then we definitely are going to catch that 1 ounce. So again, there's a trade-off, ladies and gentlemen, on your critical value. Wider confidence intervals or smaller confidence intervals. Okay, you're not quite as confident at 90% as you are at 99%. Okay, let's wrap this up, ladies and gentlemen. Okay, number 3. Number 3, explain the meaning of the confidence interval. Okay, so here we go again, ladies and gentlemen. So the meaning of the confidence interval, 90% confident means we are using a method that will capture the true parameter in 90% of all possible samples of size. Uh-oh. Okay, hold on here, folks. I got to go back and check something here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, phew. I thought I'd made a mistake. Yeah, there's the sample size is 8. Okay, so of all possible sample size, let me spell the word of right first. Sample size, period. Boom, I'm done. Okay, 90% confidence means we are using a method that will capture the true parameter in 90% of all possible sample sizes. Samples of size, of this size. No wonder I'm like confused, of this size, which is size 8, sample size of 8. Okay, sorry about that. Okay, and then I think there's one more thing. Yep. Determine the sample size you would need. Determine the sample size you would need to estimate mu within 0.001 at a 90% confidence level. Okay, ladies and gentlemen, remember we solved for n earlier in the other video. So n is going to equal, okay, do you remember what it's going to equal? N is going to equal the margin of errors on the bottom, right? And the z star times the standard deviation and all of that squared. Again, this is not given to you on a formula, okay? But what you should know is, ladies and gentlemen, the margin of error, okay, is the z star, you should know this, times the standard deviation divided by the square root of n. And then what I did was I solved for n, right? I got n by itself, so that's what it looks like. So here we go. All right, so the z star, again, is the 1.645. I'm going to multiply that to the 0.005. And the margin of error that we want, ladies and gentlemen, is 0.001. Okay. All right, let's see, calculator time, and let me get this cleared. All right, let me move this over here. So I'm going to go ahead and, did I put the square on that? No, I didn't. We got to square that, folks. All right. So I'm going to go parentheses. 1.645, forgot that 5, times, I do not need to use the parentheses inside that. I can just go times 0.005 and then divide it by 0.001, close it, square it, enter. So, ladies and gentlemen, it says 67.65, okay, 67.65. But remember what I said in the other video, at least I think I said it, okay, we always round up. We don't follow our rounding rules, we just always round up. So our sample size, ladies and gentlemen, we need to have a sample size of 68 candy bars. If we want a margin of error within 0.001. That's just, I solved that using simple algebra, ladies and gentlemen. Okay. Again, here's our margin of error. I solved for n. I would just memorize that. And then plugged the numbers in, found n. Boom, I'm done. All right, ladies and gentlemen, that took a little bit longer than I wanted it to. Okay, but again, I have to do what I need to do to get as much across as I can with everything that we're doing. All right, ladies and gentlemen, see you soon.